All right, Bismillah ar Rahim. So let's get started. This is part three um, of chapter 16, and hopefully we should be able to finish this inshallah today. So we're talking about monosaccharides. We talked about glucose last time. And we talked about how glucose um, primarily exists in this ring form, the pyranose ring form. I asked you guys to look at this video, this link as well, please, right? And so we have the open chain projection, open chain structure, or the Fisher projection, and then we have the ring form, or called the Howard projection. The Howard projections are these guys, and the open chain is this one. So I told you guys to memorize, of course, glucose, right, in both the formation, and we talk about how this is on the right hand side, and and then you go up and then go across, and so on and so forth, right? Okay, and then we talk about the open ring. If you have it's up, then down, and up and down, and the last one, carbon number one, is down, is because of alpha, it's down. If it is up, because of beta, it's up, right? Okay, now moving on, we talked about the 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 pyranose forms of glucose. They are more stable 99% of the time. It exists in that configuration, and the beta is more stable, so beta is 64% as opposed to 36% here. 36% for the alpha form, right? And this is roughly less than a percent here. Okay, and then very quickly, last time we talked about how fructose, which is a 6-carbon keto sugar, is a 6-carbon keto sugar. Carbon number 2, you have the oxygen nucleophilic attack from there, forming a ring, and then you have this ring form where you have CH2OH on both sides, and if OH is down at carbon number 2, so this is number 6, 5, 4, 3, 2, 1 at carbon number 2. If OH is down, it is the alpha form, and so on and so forth. Okay, so and then the very last thing we talked about, again, you have the ring open chain as well as the ring forms, the alpha versus the beta, and then we talked about how you can other isomers, and we talked about the galactose. And now galactose is a 6-carbon aldose sugar. This is, you should know this. This is shown here what it looks like. This is the aldehyde, carbon number 1 all the way to number 6. The D form is there, and again for glucose, if you go up, there should be an OH for glucose, and it's not. It's actually OH is on the left hand side, and that is the only difference between galactose versus glucose, right? So please make sure you guys know this, and that is actually shown reflected in the Howard projection as well. This is number 6, carbon number 6. Um, let me see, to read that. So it's carbon number 6 here. You have 5, 4, 3, 2, 1. So 6 OH is up. Then it should have been down here. It should have been here for glucose, and it is not. It is up there. So that's the only difference. And then up, down, same as glucose. Okay. So it's all this very quick review. We talked about the difference in carbon number 4 for glucose. So this is 6, 5, 4, 3, 2, 1. 6, 5, 4, 3, 2, 1, and that is the difference between glucose and galactose. Okay, so just make sure please you guys memorize that. Now we move to a 5-carbon sugars, and the 5-carbon sugars, again, the one I told you guys to memorize was ribose. This is the aldose sugar. So where all the OHs are on the right hand side, and this is a D form here, right? And again, you can have the same sort of thing where so you have 1, 2, 3, 4, and 5, and you get this kind of attack from carbon number 4 hydroxy group, forming a 5-membered ring. And again, just like all the OHs are on the right hand side, we have all the OHs on the down position, right? And it is a very simple structure. So you have CH2OH up, then down and down. And then if you have OH up or down, that's where it's shown here. If it is up, there's going to be beta. For the alpha, OH will be here for the alpha form, right? At the down position. Now, of course, this is ribose. This is ribose, but you can also have deoxyribose. So riboses are found in which nucleic acids? RNA, right? And deoxyribose are found in DNA. So if you have a DNA nucleotide, then you have deoxyribose, and the deoxy really is at carbon number 2, so we call it 2' deoxy. So if you were to look at the numbering, this is number 5, 4, 3, 2, 1. So this at position number 2, that's where you have the deoxy form. There should be no oxygen or just a simple hydrogen, and you will see that in the subsequent slides, right? Okay, now when we're talking about sugars, it turns out sugars have the ability to get oxidized. So sugars have aldehydes. Now, if you remember basic organic chemistry, if you have aldehydes like this, right? Um, if you have an aldehyde group like this, these can be oxidized, right, to carboxylic acid, right? You can get carboxylate or carboxylic acid groups, or they can be reduced to alcohols. So there's no space here. Uh, so let me just write it. I'll write it here sideways. So if you have an aldehyde, they can get oxidized, and put O here and O minus like carboxylate, or they can get reduced to alcohol, right? CH2OH, like primary alcohol. So primary alcohols can get oxidized. So you can say primary alcohols can get oxidized to aldehyde, and they can get oxidized to carboxylic acids, right? So we know that. So if we have um, if you have uh, if you have this oxidation, so let's see, if you have the aldehyde groups here, and this is getting oxidized to carboxylic acid group, if they're getting oxidized, then they will reduce something, right? That's where the redox goes. If something is getting oxidized, then something else gets reduced. So in terms of what you can do, you can add a copper 2 solution, and copper 2 is normally a light blue color, right? And in this reaction, aldehyde is getting oxidized, so copper 2 must get reduced, and it gets reduced to copper 1, in fact, right? In the form of copper 1 oxide in the form of this guy here, and that's a red-orange color. So this is a simple test you can do for the presence of any aldehyde group. Now, it turns out the most common aldehyde that you find in our body is basically monosaccharides, aldo sugars, right? Or specifically glucose, right? So glucose is found in the body a lot, and this is the primary it's the primary uh, aldehyde in our body, which is glucose, right? Glucose in the blood, especially, or in the urine, for example. And so glucose can get oxidized to a gluconate, right, form of the sugar, which is oxidized carboxylic form. And if you put copper 2, then the copper 2 can reduce to copper 1. And this was actually used as a test to measure glucose in urine. So in the old days, if you wanted to know if somebody is diabetic and they have sugar coming out of in the urine, what you could do, you could literally take their urine and put a little bit of copper 2, alkaline copper 2, and if there's aldehyde present, the aldehyde will get oxidized and the copper 2 will get reduced, and you get copper 1 red orange color, and then you'll say, oh, there's a lot of sugar, a lot of glucose, or a lot of aldehyde present. Now this is called, so glucose is called a reducing sugar, right? Why? Because it is getting oxidized and reducing copper 2 to copper 1. So the aldehyde groups of aldoses, all aldoses are oxidized by a reagent which is called Benedict's reagent, which is basically an alkaline copper 2 solution. So the word Benedict, please remember that, is basically an alkaline copper 2 solution. And as the reaction proceeds, the blue color of copper of the reagent fades, leading to copper 1, which is a red orange precipitate, right? And this is so. Based on this, all aldoses are reducing sugars, not just glucose, but any aldose sugar would be it would be a reducing sugar. So glyceraldehyde, ribose, glucose, galactose, all of them would be considered a reducing sugar. Even deoxyribose would be considered a reducing sugar because it has an aldo group, right? Okay. Now, of course, so it turns out, as I was saying, if you have aldehydes, so aldehydes can get oxidized, right, um, to carboxylic, right? So if you have a keto group, for example, can ketos be oxidized? So that's the question that we're going to ask in the class tomorrow. If somebody can answer that, right? Can ketos be oxidized to carboxylic acids? So let's make it look nicer here. So the question really is this: if you have a ketose, right? So this is the ketone group. Can a ketone be oxidized to carboxylic acid? Like that, right? Is that possible, right? And we will see this, and the answer really is no, right? And so only aldo sugars should be reducing sugars, only aldo sugar. But if you look at here, this slide is saying is all monosaccharides, right? And in fact disaccharides. We'll talk about disaccharides, except for sucrose, are reducing sugars. So all monosaccharides. So this slide is saying, right? This slide is saying whether you have aldose or ketoses, they're all reducing sugars. So how about ketones? How is it possible? How can you have ketone, right? Because ketones normally cannot get oxidized. So how can they? Well, it turns out if you have fructose as a keto sugar, right? So this is fructose, right? And this is the keto sugar. It turns out it can go isomerize through this ene diol. This is the ene diol configuration, and then it can take an aldo form. So fructose, which is a keto sugar, can essentially become glucose through isomerization reactions, and this is actually slow, but it does happen. So fructose can actually become glucose. So all ketoses, technically, ketoses can actually become aldoses, and then when they become aldoses, they can act like a reducing sugar. That's how they are. So every monosaccharide, which is aldose or ketose, are called reducing sugars. Okay. So another test of reducing sugar is by a different reagent, and this reagent is called tolerance reagent. Now, tolerance reagent is also called the silver mirror test. Those of you who have taken organic, silver mirror test, right, where you have any aldehyde. So of course primarily it's formed in this state, but there is a small equilibrium to reach the open chain. If you have the open chain aldehyde, so this opens up to aldehyde. So if you have a silver +1, it can react to so you can get again oxidized to the acid form, and then that silver +1 gets reduced to a silver elemental form of silver, and you can get a silver mirror produced. So you can get oxidation of aldoses to give you a silver mirror. But again, with aldoses, ketoses can also react as well. The same idea that you can have ene diol rearrangement and isomerize to ketose, and likewise ketose can become aldoses. Okay. Now we talked about ribose last time. So this is deoxyribose. Now deoxyribose is very similar to ribose. Again, I'll draw the ribose here. So the ribose form was 1, 2, 3, 4, 5. The last one I put CH2OH, and this is aldo sugar like this, and I have OH, OH, OH. This is ribose. This is D-ribose. So the the deoxy part is 2 prime. So 2 is carbon number 2, which is basically 1, 2, 3, 4, 5. So at this position, at the position number 2, right, the OH is missing. OH is missing, and that's why it's called deoxyribose, and that's shown here as well. This is number 5, 4, 3, 2, 1. So at carbon number 2, the OH is missing. OH is missing. Okay, so that's deoxyribose. and we call it a reduced sugar. It is reduced. It is, again, please, it is, we're not talking about reducing. Please make sure you know the difference between reduced and reducing, right? Sugar. Okay, now we'll move on to disaccharides. Of course, disaccharides. So all the carbox monosaccharides. You have you know, they can react, and the anomeric OH can react. So the anomeric OH can react with other alcohols, right, to form a glycosidic bond, which is basically an ester, an ether bond. So which is, you know, COOC bond, right? And actually it's called a full acetal. It's not ether because you have this on the other side, you have O here as well. So it's in the these bonds are called hemiacetal. Hemiacetal. Oh, it's mentioned here. Okay, and this ball is called full acetal. Okay, so you have this reaction here, and as you would expect, water is removed, and this water removal is, again, we see this with two amino acids coming together to form a peptide bond, right? A condensation reaction, water comes out. Or we see it with fatty acids reacting with glycerol to give you triacylglyceride or phospholipids. Again, water is being removed. And now here in this glycosidic bond formation, and this bond is called a glycosidic bond. This is a glycosidic bond. That formation, again, you see water is being removed, released, right? Water is lost. Okay, and of course, now it's reacting with methanol, but methanol is not really relevant. What is relevant is that you can have glucose here and any OH containing molecules. You can have another glucose sitting right next to it, and they can form this bond, and that's what happens, right? So you have alpha D glucose and another glucose molecule that has, you know, tons of OHs, right? So any of those OHs can react with this alpha anomeric carbon here. So if you have two glucose right next to each other, they can react and they can form this full acetal group. So COC form, and that is called a glycosidic bond. Glycosidic bond, right? And with two glucose linked together, uh, this bond has a name, and we call it alpha 1,4. So alpha from the fact that this first is alpha OH. So there was an OH here, and this was alpha, right? And then the reaction was from carbon number 1. Again, you have the numbers are mentioned here. This is carbon number 1, and it's reacting to carbon number 4, and then you have this water being eliminated, right? And COC bond gets formed, and this is called a alpha, because an alpha 1, that's this OH, 2 carbon number 4, right? The alpha 1,4 glycosidic bond. So we say you have two glucose units linked together. So if you have two glucose units linked together by alpha 1,4, this is alpha 1,4, that is called maltose, right? So maltose is a dimer, it's a disaccharide of two glucose units, right, linked together by alpha 1,4 linkages, right? That's what maltose is. Now, of course, if you look at the end here, this part, this is OH, free OH. This is the anomeric OH. It's up. If it is up, we call it beta. So what I've drawn here is the beta maltose, right? If I say draw alpha maltose, then at this position I can change it. I can put an alpha. So if you have two alpha glucose linked together, they'll give me alpha maltose. But if I have alpha and then a beta, you get a beta maltose. Okay. Right. So shown that. Okay. Now you can get again two glucose also linked together, but linked together, so glucose plus glucose, but linked via a different bond. We call it a beta glycosidic bond. So in fact, it's a beta 1,4 linkage, not alpha. If you have alpha, you get maltose. If you have beta 1,4, so what does that mean? It means at carbon number 1, you have to have a beta, so OH meaning up. So you have 6, 5, 4, 3, 2, 1. At carbon number 1, you have OH up, and it's going to react with carbon number 4 of another glucose. So this could be, this is in case of, so you have two beta reacting. So this is going to react, and what has to happen is, this OH and that OH, and the water comes out, and the one O stays in the middle. And since you have this bond up and one bond down, then you have to have up here and down here, and then the O that you have, it stays in the middle, and you get this really weird looking bond, and that is a beta 1,4 glycosidic bond. And what you get a different disaccharide called cellubiose. So maltose is different, maltose versus cellubiose. So please make sure you understand the difference between the two. In maltose, you have glucose, alpha 1,4 glucose. In cellubiose, you have glucose, but you have beta 1,4 glucose, right? So make sure you understand the difference between the alpha and the beta glycosidic bond. That gives you different things. Now, of course, if you recall, I think some of you may know that maltose, so maltose is found in starch like rice and French fries and so on and so forth. Cellubiose is found in cellulose, and cellulose is found in grass and so on and so forth. So this bond is the difference between French fries and grass, right? French fries has starch, the potatoes have a lot of starch, and they're based on is glucose and glucose linked together, right? And you can digest it, we can eat it, we can enjoy it, but grass is also glucose and glucose, but it's beta 1,4 linkage, and we cannot digest it. We can't eat that, right? So that's the slide here, highlighting the difference between easy to digest starch. Starch has 1,4, 1,4, 1,4, and of course these are all glucose. This is glucose, and this is glucose as well. Right? This is glucose. This is glucose, but this is cellulose. In cellulose, you have beta 1,4, and in starch you have alpha 1,4. Right? So if you have many linked, so many maltose. So starch is basically many maltose units linked together many times, and cellulose is cellubiose. So and now what we've done, we have moved on from disaccharides into polysaccharides, but we're showing you that we can digest, we can eat starch, and we cannot eat cellulose, right? Most of us cannot eat grass, and the reason, of course, between the two, between nice bread and nice grass, is that we don't have the enzymes. So we have the enzyme that can digest the alpha 1,4, and we don't have the enzyme that can digest the beta 1,4. The beta 1,4 digesting enzymes are not found in humans. That's why we cannot eat grass. In fact, that's one of the reasons if somebody wants to lose weight, they can eat lettuce, and we can eat a lot of lettuce. We don't get any calories because we don't break it down. Our bodies cannot break this down, and then we don't get calories. Whereas if we eat rice and bread and things like that, our bodies can break it down, and we do get calories as in the form of sugar or glucose. So again, please make sure you understand this. There can be different types of glycosidic bonds shown here. This is down, so alpha 1,4. This is this is down again. This is alpha again. So we have alpha 1,6, 1,4. This was going up, so this was a beta, right? So you have beta 1-to-1 glycosidic bond. And in this case, please note what they've done. They have flipped the glucose, so it's flipped. So it is not alpha, so it's actually also beta, but they just flipped the two molecules. It's difficult to see what they're doing here, but just draw it like this. It's a beta 1, so it's beta 1 to beta. This also 1, so we call it beta 1 to beta 1. So beta 1 to 1. So they have different kinds of bonds. Okay, so we'll talk about another disaccharide, which is maltose. Sorry, which is lactose. So we've talked about we've talked about, sorry, we've talked about maltose. What's happening here? So, okay, we've talked about maltose, number one. Then we talked about cellobiose as number two. Now the number three, disaccharide. We're talking about disaccharide. So disaccharide we'll talk about is lactose. So lactose is formed by joining of beta D galactose now to a glucose unit. So beta galactose to an alpha glucose, and again it's a beta 1,4 glycosidic bond. I think the next slide shows that. So this is beta galactose. Please keep in mind position number 4 is what's different here, and OH is up here, so this is a beta form, and here OH is up, so this could be a beta as well. So they can react together, and you get a beta lactose, right? Beta lactose. So you have beta 1,4 linkage between galactose and glucose, right? If I say please draw the alpha form, then you should be able to draw the alpha form. So let's draw alpha lactose. So you draw. I'm gonna draw two molecules. First, I know I need to have alpha. So if I say alpha lactose, so I must draw alpha glucose here. OH down. So CH2OH, up, down, down, up, down. This is my alpha glucose, right? Alpha glucose. Okay. Now I'm gonna draw galactose, but suppose I forget galactose. I'm gonna draw first glucose. Glucose is one up, down, and I need to have a beta glucose, beta galactose, sorry. So I put beta will be OH here. Now what I've drawn is glucose. To draw galactose, carbon number 4 has to be different. So I come here and I just delete that part and I put OH on this side. So this is my galactose now, and I'm gonna get this reaction going, right? To get that reaction going, again I remove that, I remove this H here, I remove this here, in fact I remove all of this, and I join them with a line that goes like that, right? Or as they have drawn, or I can draw one up, one down, but this is totally fine. This is perfectly fine to draw it like this. This is perfectly fine, right? And then what you get in a alpha lactose. So alpha lactose. Okay. And sucrose is the last one. So this is number 4. So sucrose again is formed by it's a dimer, disaccharide. You have alpha D glucose with a beta D fructose, right? So let's see how that looks. So you have alpha glucose. You just draw alpha, and then you draw beta fructose. So beta fructose, OH has to be up, and then CH2OH, CH2OH, and you get this glycosidic. So we say alpha 1 to beta 2. That's what this bond is. Alpha 1 to beta 2 linkage, and this is called sucrose. It's a disaccharide between glucose, but alpha glucose, and beta fructose. Okay, so I'll stop here with this, and then inshallah we'll see you guys tomorrow, and see if you have any questions. All right, I'll see you guys tomorrow then. Assalamu alaikum.